his interest. I was saying it's a pleasure to have here Giulio Biroli, is visiting us from the École Normale Supérieure in Paris. Giulio is very well known for his many contributions to statistical mechanics, in particular the theory of disordered systems, but he has also a very active line of research in diverse topics like machine learning, ecology, and etc. I've always admired his work because of the blend of sophisticated theory and also intuition. And I'm delighted that you decided to stay here. I'll be here until Friday. Yeah. Thank you guys for coming.
So thank you very much for the introduction, and I'm happy to be here. It's my second time in Chicago, and I really enjoyed it very, very much. Please, on the back, tell me if I don't speak too loudly. I have a tendency that we have a relaxation time, so you have to remind me.
It's a professional thing. This is a slow relaxation.
It's not so slow. All right, so today I would like to tell you about a recent work. It's recent, but we work on this for actually 2 or 3 years with at the École Normale, with Stéphane Malard, who is applied mathematician, computer scientist at the École Normale. And two, well, they were postdocs, but now they're both Misaki Ozawa is a CNRS in Grenoble, and Tanguy Marchand is working in the private sector. So my talk is about relationship between renormalization group and machine learning. I'm not able to change the slide. That's the important. All right. So let me tell you what is the context. So the context is about generative models and sampling. So I mean, more generally, you can think about in machine learning, but in machine learning, I think one of the great and impressive success of deep learning is to have generative models that, roughly speaking, and then we really cut the long story short, because I think you have already seen this kind of things. They are able roughly to transform something which is white noise in some. They are trained to transform something which is white noise in something, for example, in images, images of faces, images of cats and dogs. I mean, if you apply this to physics, they can generate configuration, for example, of the Ising model, if you like, in statistical physics, or they can generate, for example, images of the distribution of density in the universe. So while they can help you to generate meaningful configuration. And so in physics, if you think to physics or in general, also in applied math, in scientific computing, they can help you to sample new configuration. So this is the context. So now the thing which I find very interesting, on which I've worked in the last year, is that these models, the generative model, and more generally, artificial neural network, are not well understood. It's a fantastic scientific challenge to understand why they work. They clearly work, at least to some extent, with impressive results, but it's not clear why. And in a sense, they are very simple. It's in the sense that, as a physicist would say, like we would say the Ising model is simple, but then it does impressive things when you study it. What they do are successes in nonlinear transformation. Of course, I oversimplifying, but this is what they do. They do many nonlinear transformation. They have a lot of parameters. You train the system, so you fix the parameter in such a way that they do what they want, what you want on a training set. And then they behave very well on the test. So this is the context. And just to tell you why I think they're interesting. So they're interesting in the sense that they do something which is impressive, for example, in image, on images. But now I think all of you, it has been so popularized, how good are this kind of artificial neural network. I think it's many scientists try to play with ChatGPT. I don't know how many of you. Today was released GPT-4, which is just a new version. Now you can give an image instead of writing a text, and it will give, and you will do what you want. But I think the interesting thing is, of course, it's something that will be more and more important in our society, but it's also important to do science. So in science, well, they have been applied already, for example, if you give configuration to recognize when a system has a phase transition, they have been actually used to put bound on the cosmological constants. And there are very many ideas that they can be used actually to do sampling in cases in which something is very difficult. So many of us that do physics know that when in many cases you do a numerical simulation, when you try to do a numerical simulation of a complex system, it can take a very long time to get a meaningful configuration, let's say an equilibrated configuration. And now, if you have this, let's say, black box that you enter white noise and they give you a meaningful images, you can think that maybe what they can do is that they can transform white noise in configuration in samples that are really meaningful and are almost typical or almost equilibrated. And there are ideas or proposal, for example, they can do that, for example, in constructing folded proteins. And well, there are many ideas that this kind of advance in applied math and computer science can be very useful actually to do new something scientific sampling in scientific computing. So clearly they are really successful. They have a lot of potential in science, but still I think there are many questions that are open. So for example, one interesting question for us is how faithful actually is the representation of the probability distribution that this generative model generates. So, well, if you have faces of cats and dogs or image of cats and dogs, you don't know what the probability distribution is. So in a certain sense, you don't care, even if one should probably care for many reasons. But if you want to use it in physics, well, we know in some cases what is the probability distribution. And we would like to know, well, even though with the eye, this configuration might look good, what is this model are really sampling the correct probability distribution? The other thing, questions that is not so much which we don't know is what are the limitations and the scalability. So imagine that I'm able to generate images with a certain size because well, it takes some time to train the model and then it takes sometimes actually to produce the image. Now, if I take an image which is 10 times larger, what's going to happen? It's going to take 10 times more to train the model in terms of time, or it's 100, it's 1,000. Similar thing once I train the model, if I want to produce the image, is it going to be fast if I multiply by 10 the image? And this, of course, are things which are relevant for in general and the application of science. Then there's this question, which is very interesting to me, is that, well, maybe this image can seem complex, but I work a lot on problems which have slow dynamics, in which the real challenge is produce configuration which are equilibrated, and which takes a long time if you use physical dynamics, like Monte Carlo damping, Langevin dynamics, molecular dynamics. This method could circumvent completely this difficulty and be able to produce a good sample, even in systems which have a very slow dynamics, as is suggested in some cases. And then even if this answer is of all this question is yes, well, we don't know actually what the answer is, but even if it's yes, we really would like to know what's the theory behind, why does it work, why it's possible to do so. So what I want to do today is actually to address this question in a particular case. So what we're going to do is we're going to focus on images which come from physical models. Now, physical models means models which come from statistical physics, and I will tell you what these models are, and actually and data which come from simulation of cosmology. And so this is images from physics that are not computer vision. And within this set of training data, what we want to do is that we want to find an approximate representation of the probability distribution. And from this approximate representation, so which is a generative model, we want actually to be able to sample new configuration and also obtain the energy function. Of course, I mean, being a physicist, I mean, it's important not just to generate new sample, but you want to have some approximation on the energy function, because from this you can really learn physics. And we're going to do this combining ideas which come from physics, renormalization group, and computer science, and particularly wavelet and sparse representation. And we will construct a generative model, which we call the Wavelet-Conditional RG, that will allow to do this. So within this scheme, which has important relationship and similarities with models, generative models that are used in computer science, but it's different. It's we construct really a new generative model. What we can show is that we can do indeed efficient training and sampling. What I mean by this is that even if I take the system at the, for example, a ferromagnetic model at the critical point, you know that if I take the system larger and larger, there is what is called critical slowing down. So if you want to sample configuration with Monte Carlo, for example, you take a longer and longer time. What I'm going to show is that now, with this method, actually, the time scale to get the new configuration is order 1, even at the critical point, and we will explain why. And also, if I want to train the system, also the time scale is of order 1. So it doesn't scale with the system size. Then I will show you that it's possible to reconstruct the energy function. And well, I think the important point is this is one of the first instances in which you can understand how this method works. And the reason why they work is that they combine property of the structure of data with property of, let's say, the architecture or the algorithm that we are using. So these are the three outcomes of our analysis. So if I go back to these four questions, I will be able to answer these four questions in this precise case, which is, of course, it's not this case here, but it's the case with images which come from physics. But then at the end, I will also tell you more about more complex images, so which we are more complex in terms of physics or more complex in terms of really, if you try to have, for example, faces or images of cats and dogs. Okay, so that's the idea. So again, if you have questions, do not hesitate. Yeah.
So I'm trying to understand the big picture. So you first generate a bunch of samples. You know, I give you some Hamiltonian like the Ising model, and then that's what I use as my training data. And then the question is to give out a new, say, Ising configuration.
Yes. So it's really here now. The idea is just to explain. So for the data which come from statistical physics, what we do, and this is more a test than, I mean, it's a test that the method works in a very non-trivial case. What we do is that we take the energy which corresponds to the two-dimensional discretized field theory for the ferromagnetic phase transition. So this potential V has the usual double well form. And this is known that if you change the temperature, you change the form of V, you have high temperature, the system is disordered, then you have a critical point, and then you have a low temperature phase. So what we do is that we start with this energy, we generate many configurations, then we forget about the energy. We don't have the right to use it anymore, this knowledge. What we want to do is that just from the data, we want to construct a method that is able to sample new configuration, and also that tells you what the energy is. And then we want to do it, and we do it in this case, which is really the test for us, how the method works, in a non-trivial case, because there is a phase transition, there is symmetry breaking, there is critical slowing down at the critical point. And then we apply to cosmological data. So in cosmological data, you have actually simulation that simulate dynamical equation out of equilibrium. And from this, we get the data. Then we apply the method, and from this, we generate new configuration. This is actually, it's a problem that is very important in cosmology, because it helps to constrain the value of the cosmological constant, and then it will be used also in connection with the experiments that will come from the Euclid. So in this case, the system is out of equilibrium, there is no underlying energy, but we can still get an energy which has a role of an effective energy, since the system is out of equilibrium. So if you want, it's the log of the probability of the system, then you can call it effective energy. So in practice, so we use images which are 32 by 32, just like this was actually, now we do much bigger. Then we use something like 10,000 images, and then our model, just to give you the idea, consists in 1,250 parameters. So if you're used to deep learning, you already see a big difference in the sense that the even number of images that we use is not so big, and especially the number of parameters is not so big. And this is because we have physics in mind, so we can constrain a lot actually the number of parameters and the model that we use. And so, well, again, as I told you, the aim is from the data, we want to approximate the probability distribution, so be able to generate new sample. We want to obtain the effective energy function. And this is really the two things on which I will focus, but then I will tell you more about more complex cases in the conclusion, both physics and from computer vision. Okay. So if the idea is okay, now what I want to do is, well, tell you a little bit why there is this link between renormalization group and machine learning, and in practice, what we really do. So renormalization group, I don't think I have to tell you anything about it. So it's renormalization group is this fantastic technique that was developed in the 70s, which allow you really to transform, to change scale, and to transform a probability distribution of a many-body system to the probability distribution of the many-body system, which is coarse grain of a certain scale. And now deep network is, as I told you, there are these algorithms are successive nonlinear transformation of one layer after the other. And there is this idea that exactly like RG, what it does is that with coarse graining progressively from, it's a multi-scale method which go from microscopic scale to macroscopic scale. There is this idea around, especially from physicists, that somehow what this method, this deep learning method do is also working in a hierarchical way, in which the first layer just work on the very fine scale properties and the last layer work on the very large scale property. I mean, in a sense of this is a triviality. We know that the last layer is what is going to tell you whether the image is an image of a cat or a dog. So of course it's a large scale property, but it's known also that if you look what the small layer do, they really try to recognize, for example, edges or very microscopic property of the image, and it's only the last layer that look at the big features. Now, this is an idea, but of course, is this just, I mean, an idea is just an analogy, or there is a stronger connection. And what I wanted to show you today is that within our model, and for the data that we consider, there is really a very strong connection between it. Okay, so while renormalization group, I think it's this is just to recap, but I think here in this audience there is no need to recap. So this is just, let me just go quickly in order to set up the notation. So this is the image of the Ising model, and this will be a video just to remind you what the RG does. So what the RG does is, in essence, is the way to change scale. So you have the probability law at a given scale. So this is my notation. This is the length at the scale j-1, which is defined in this way. And what you want to do when you do RG, you want to get the model defined on this length, the model defined on this length. So the way you do it is that you decompose generally the field in what we call the coarse grain part and the small scale fluctuation or the fast degrees of freedom. And then if you want to do RG exactly, you integrate out the fast degrees of freedom or the more scale fluctuation, you get the probability at the scale. So you have change scale of a factor of 2. And from this probability, if you want, you can read also what is the energy on the larger scale. So you have in this way a flow, which is here in the discrete map of the energy from one scale to the other. And just to remind you, so if you do oops. So this is the more video. So here is what happens if you do it below TC when you change scale, while at very high, when you go to very large scale, since you go to the order, complete the orders, you kill completely the small scale fluctuation. So the configuration is typically ordered, no more fluctuation. So here, if you do it here at high temperature, still at the beginning, you had some correlation length. And now you coarse grain, you coarse grain, you coarse grain. And at the end, you will get white noise because you have coarse grain to a length which is much larger than the correlation length. And the nice thing, which is what as physicists we like a lot, is that if you do it at a critical point, if you coarse grain a little bit, you forget about the microscopic properties, but then you reach a fixed point at which the system is invariant. And so the probability distribution here is trivial, here is non-trivial, and it's characterized, is what characterizes the critical point. Okay, so this is just a quick recap. So again, so there is something that on which I want to insist. Of course, all of you know the renormalization group, but there is one thing which is really the crucial element of RG, which will be the crucial element also for us. So the crucial element, if you think about RG, what it does, what is the magic of RG, is that it's able to treat a singular problem. So phase transition are a very singular problem in which you change a little bit the constant, and the change of this in the system change behavior completely. Because if you change the temperature a little bit from Tc minus epsilon to Tc plus epsilon, the system really changes behavior because it goes from, for example, it breaks the symmetry. Now, in generally, well, it's well known that if you try to do perturbation theory to treat this problem, of course it fails, and you can understand why it fails because, well, you have a singular problem in which if you change a little bit the constant, the behavior of the system can change a lot. So of course, if you try to do perturbation theory, in which, I mean, you are changing a lot the value of the constant, so this is going to fail. This is well known. It's also related to the divergence in quantum field theory. Now, the magic of RG is that RG never works in an exact way. You always do approximation in RG. But the approximation in RG are legal, no problem. Whereas if you do approximation, like perturbation theory, then they completely blow up. And the reason for this, which I think is one of the most important thing about RG, is that at each scale, so RG is a change of scale. At each scale, what you do is that you always want to do, you want to integrate over the small, the field which correspond to the small scale fluctuation, what we call the fast degrees of freedom. Now, these fluctuations have no problem, they are not singular. And this is why you can do approximation in order to do this integral here. You can do approximation on the field which correspond to small scale fluctuation. This is not a singular perturbation, it's not a singular problem. And this is why actually you can do approximate RG, and then you can treat a singular problem doing approximation on the RG flow. And this is really the core also of what we are going to do to be useful for us. Yes.
So is there an assumption that the Hamiltonian is local here?
Yes.
Yeah.
Yeah. So indeed. So in usual, so in RG as it's done normally is that you always start with an Hamiltonian which is local. I will discuss also how much non-locality one can have, but it's true. I mean, especially for standardly in equilibrium phase transition, you always start saying, okay, they have an effective cost grain energy from which they start, which is local. And then you select all the possible critical points looking at local theories. Yeah.
Is that also why there's many fewer parameters?
Why
So you
you
imagine that your Hamiltonian is just sort of many copies of the same local Hamiltonian. Is that why you have fewer parameters than your model?
in our case, or I would say in our case is because we have it's a mix. It's a mix of this. It's really, I think, because we have some a priori knowledge of what we think the energy is that we should use. Okay, so now just after this reminder, let's go to our method. So in our method, we want to do something which is completely different from RG. It's actually the inverse of RG. So we have the data, and from the data, we want to construct the probability, an approximate representation of the probability distribution. So what we're going to do, well, we are going to use exactly the same idea of RG in the sense that we take the field at the given scale and we divide it in two components, and we do it using wavelet theory. So wavelet theory, if you want, is a kind of generalization of Fourier theory. I mean, it's a Fourier transform. It's a big generalization, but it's similar. So what you can think is that what you can do, and this is the non-trivial part of wavelet theory, is that you take, given a field, you can decompose it in an orthogonal way in a part which is the cost grain part, and a part which is correspond to the small scale fluctuation. And depending on the kind of wavelet that you use, then you find different bases and you find different way to represent the cost grain part and the small scale fluctuation. Now, this is an example, actually, really, it's a real space example. So this is the configuration of the IZ model. I think it's the IZ model. The 5-4 discrete two-dimensional discretized field theory at TST. And here is a decomposition. So when you go from a scale, from this scale to this scale, so it means that you go from 1 degree of freedom to 4 degrees of freedom. So for each field, you have 1 cost grain field and 3 wavelet fields. And what I'm telling you is that knowing this and these 3, it's equivalent to know this. So you can go from one to the other. And so this is the coarse grain version of this, and this is, let's say, the short scale fluctuation that you have to add in order to get to this. Now, there's one thing that I didn't learn actually when I was a physicist, and I'm still a physicist, sorry, when I did an undergraduate course in physics, but that now actually it's a way to, I mean, you can see it in an image, is that, again, what I was telling you before, the fact that when you work on the small, when you do approximation on the field phi, this fast degrees of freedom or small scale fluctuation, this field is not singular, it's well behaved. And here you see it. I mean, this field has long range correlation. This is a complicated object. This field here is almost white noise. So the fact of, I mean, integrating out this field, I mean, the fact that everything is going to behave in a good way, I mean, it's normal. And you see it visually. I mean, this is not complicated, this is complicated. Okay, so now our idea, in a sense, which is very simple, very simple, is we want to rewrite the probability distribution of many body configuration, microscopic configuration. We are going to rewrite it as a product, a cascade, in which we use this conditional probability law at each scale. So what we say is that the probability of the field at this scale J-1 I can write it as the probability of the fast component given the coarse grain one times the probability of the coarse grain component. Now for the probability of the coarse grain component, I can do the same. So this is the probability of the conditional probability of the fast component of this times the coarse grain, and so on and so forth. So here is the let's say the telescopic product that I can write for the probability of the microscopic field as a function of, well, the conditional probability of the small scale fluctuation given the coarse grain one, phi one, and so on and so forth. It's imperfect. All right, so if you do this, now the idea is that what we're going to do is that we want to reconstruct an approximate representation of this probability distribution. So what we're going to do is that we're instead of trying to do in one shot, reconstruct this probability distribution, we are going to reconstruct it scale by scale. So we are going first to estimate the probability distribution of the coarsest scale, which means just one variable. You have coarse grain over everything. Typically, this variable is just a Gaussian, so nothing difficult to retrieve, to infer. And then we are going to get to estimate an approximate representation for the conditional probability of these past degrees of freedom given this coarse grain one, and then so on and so forth. So at each scale, we are going to estimate this conditional probability. Now, if we are able to do this, then its sampling is going to be to proceed in this way. So once I learn this, and this, first I will draw this variable, ij. Then I will draw psi j, because I know phi j, so I will draw psi j from this conditional probability. Then I will draw well, all the small scale fluctuation. And once I have phi j and all the small scale fluctuation, then, well, I have the field phi 0. I can reconstruct it. Now, the interesting thing exactly in RG is that in principle, I mean, estimating or sampling can be very difficult or can be very slow. But here, because what we do, we always work on the fast degrees of freedom variable, this is not going to be a problem. So estimating this conditional probability is going to be easy, even at the critical point, even when the configuration phi 0 has very long range correlation, and sampling from this conditional probability is also going to be fast. And this is really, in a nutshell, this is why actually, if I want to sample even at the critical point, I will sample each one of these variables on a time which is of order 1, even at the critical point. Okay. So this really the idea of the method. In a sense, I could stop here. Yeah.
So this sort of assumes that you can identify the variables ordered by hierarchy by their how fast they equilibrate. So there's a lot of information in there.
Yes, I think it's the information that there is that in physical system, the fast degrees of freedom is really related to the small scale fluctuation. So really, once you take a field and you decompose it in coarse grain plus the rest are the small scale fluctuation, and these ones relax in a fast way. And I think the idea behind is that there is indeed at each scale, there is a local representation of the energy, I mean, of the dynamics or of the energy function. So which doesn't have to be general. I think it's quite general in physics, but of course, if you throw one who goes beyond physics, then maybe it's completely wrong. I'm trying to argue that it's not, at least to some extent, but or if you want to apply to things which are, I don't know, which come from biology, which there is no underlying real space behind, then of course things can be different. So I think it's the hypothesis that is behind is this comes from physics for the moment. And in physics, indeed, the idea is why the RG works. I mean, it's the same thing why the RG works. You always work on the fast degrees of freedom. I think they are fast because there is an underlying local Hamiltonian, at least for the interaction between these degrees of freedom. Yeah. Okay, so let me tell you now what the method is. The method is used. And again, it can be generalized, but for the moment, I tell you the most easy, the simplest approach. So what we do is that we really use RG as a guide. So the guide, so in RG, we do the inverse of what you do with RG. So in RG, if you remember, what you do is that you know the probability distribution, and then you forget, in a certain sense, a little bit of the probability distribution at each scale, because you integrate out some degrees of freedom, so you lose information at each scale. So here we do exactly the inverse. So that we use the data to reconstruct at each scale the probability distribution. So we have a probability distribution that allows us to describe the system in a finer and finer way at each scale. And it's because actually we use at each scale from one scale to the other, we use the data. So we retrieve more and more information at each scale. However, we use indeed this idea that at each scale, there is an underlying Hamiltonian which is local, that we can use an unlocal Hamiltonian. So I will tell you generalization of this, but when you do RG, this is what you do, is that you think that once you at each scale, you have some Hamiltonian, which is local, which describes the system. So if you use this idea, then we have a model for the conditional probability. Because you see that, I mean, if this is given by a certain Gibbs form, exponential minus h, with h given j minus 1, which is here, this is given by exponential minus hj, with an hj which with different k and different b. Then what I have is that from this I will have actually an expression that I can write down, even if I didn't, but which an expression for the model, which is give me the model of the conditional probability. Okay, so the model of conditional probability is going to be obtained if I know, I mean, this k and v. I can obtain the model which tells you how the probability law for the psi. So what I have to do then is to estimate by maximum likelihood from the data this h bar, which is, well, it's obtained from this h, which govern this conditional probability. Now, this is the first thing, is if I know how to estimate this h bar from the data, then I get the probability law of the conditional probability law. If I want the energy, I have to do something more, in the sense that what I will have to estimate, I will have to estimate actually what the normalization constant of this free energy fj. So the fj is just the integral of exponential minus h bar over psi. And if I know f, then you see that if I know h bar and I know f, and I use this law here, then I will get the energy in this way. It's just the sum at each scale. I sum h bar j minus 1 minus fj, and then I put the larger scale. This allows me to reconstruct the microscopic energy using the interaction energy between small scale fluctuation at each scale. So what we do in practice, and I will tell you a little bit more about this, is that from the data, by maximum likelihood, we get this h bar. And then this free energy here, this free energy, we give a form to the free energy. Because in principle, if we know h bar, well, we know f, but h bar is something complicated. If I integrate over psi, f will be a very complicated function. So what we do is that we also do an ansatz on the form of f, which is going to be this form plus this term. So if you forget about this term and you use just this, what you get, what is interesting is that once you do all this sum here, at the end, you get this energy. So you get the form of the energy, which is local on the microscopic scale. Now, if we add this, which is just a local term on the scale j, what we get at the microscopic scale is an energy which is non-local. So this, I think, is another, with respect to the question that was asked before, is that what we do really, what there is in the model is that we use a model that is local at the scale j on the small scale fluctuation. So the field which corresponds to the small scale fluctuation interact locally at the scale j. This actually can give energy function which are non-local. And I think really the key of the underlying hypothesis of the model and the RG is really that the interactions are local on the scale j. This can give rise actually to energy, allows also to create energy which are non-local on the microscopic scale. Okay, so a little bit more technique, and then I will show you the result. So as I told you, well, the way in which we estimate from data, so we have a certain expression on this h bar. Now this h bar, if you think about it, we rewrite it as some parameters, exponential of minus some parameters, which multiply some function of f. And the way to do it, just to not be too abstract. If you think about, for example, a term like this, if I bring the phi on the other side, I will have a parameter which multiply a function of phi. And so this is how it goes. So we do it for all the terms. And once you write in this way, well, you can just obtain this parameter, minimizing what is called the Kullback-Leibler divergence between the true distribution and the approximate distribution, or maximum likelihood estimation. It's a very general method in influence. And when you do this, well, what it means doing this is that you do a gradient descent on the parameter theta, where the driving force is the difference between the moment computed with the true distribution and the moment computed with the distribution P of theta bar. Once these two moments are the same, so once the theta bar are such that while these two moments are the same, then the evolution stops. You can also show that this evolution is convex, so there's just one minimum. If you take if you take a step which is small enough, you always achieve the theta that at least these two moments are equal. So this is what you do. And then to approximate the free energy, well, you just do a regression. So I show you that there is a special form of the free energy that we use. And then when we regress it, so we do this by Monte Carlo simulation, and then we regress the form that we use. If you want to know more about the technique, I will tell you, but I think this is enough already. Something that I want to tell you is some theory before showing the result is that, so this is really about why the system is easy to train, also at the critical point, also in presence of long-range correlation, and why it actually you can sample fast from using this method, even in presence of long-range correlation. Now, first thing is about the training. So when you study this gradient descent associated with maximum likelihood, what really matters is an Hessian. So it's an Hessian that controls how small you have to take the time step or the learning rate. Otherwise, the system will explode. Now, this is controlled by a certain Hessian. And this Hessian, actually, if you look at what it is something, well, it's related to the correlation function of the system. Now, this actually explains why if you try to do training without using this multi-scale method, if you just train, you just say, okay, I know that the probability distribution of phi 0, I rewrite it like exponential minus a certain energy. And then I try to estimate the parameter of the energy. If you do this, well, this is going to be very bad. We know that it's going to do very bad. It's a singular problem. So it means that, for example, imagine if you do a small mistake in the parameter, which is the temperature, the behavior of the system is going to change very much, which means that you have to be super precise on when you do the gradient descent, when you're changing when you want to fix the temperature. And this is why actually, when you are exactly at the critical point, you should be infinitely precise. So it's not going to work. Now, and this is related, if you look at the Hessian for this problem, so this is really related to the fact that you have long-range correlation to the system. And the Hessian that you find in the model, which is the Wavelet-Conditional RG, contains correlation function, which are the correlation function of the field psi, the one which was just white noise. And it's because actually these correlation functions are short-range correlated that one can show that the Hessian which is associated is stable in terms of applied math. So the largest and the smallest eigenvalues are close and they're not very far, which makes the model the training and the gradient descent of the parameter theta will make it fast. Then, well, the other thing about the MCMC, well, the MC, if you want to now to sample, what you have to do is that, well, you have to sample many fields psi. And then again, if the field, what is known is that what makes sampling slow, typically a long-range correlation. Because if you have long-range correlation, well, the Monte Carlo Markov chain has to break this correlation in order to equilibrate the system. So to get a new equilibrated configuration, it takes a long time. Now, if you just, what you sample are fields which are short-range correlated, the time scale is going to be fast. And this is the reason why actually our method is fast, because each time we sample a field psi, which is short-range correlated on the scale at which it is. And so while this we can actually, now you can ask how much we show this. So we, of course, there is a simple case, which is the Gaussian free field theory, in which everything can be rigorous, really rigorous in mathematical sense. And instead, otherwise, we can do it using RG and perturbation, just RG theory for the phi-4 case. So this actually allows us to have a method in which the convergence in time for n degrees of freedom is really optimal in a computational complexity sense. So the time scale is over 1 or over n, depends on how you measure it, even at the critical point. So now, well, let me show you results so that everything I hope hopefully will be clear. So the results of the data is this, remember, discretized two-dimensional field theory or cosmological images. And let's start from the first. So here is an example. So here we train over configuration. These are samples from the true measure, so the true system. And here are the, just three examples of the generated ones. High temperature, critical point, and low temperature. Sorry, it's a constant. High temperature, critical point, low temperature, critical point, and high temperature. Yeah.
So this is a trivial question. So when you train, you sort of do this inverse RG to sort of get a more microscopic Hamiltonian, and then to generate, you reverse it back and you sort of get back to the scale.
Sorry, say it again.
So how do you generate the images from your?
So the way you generate, you first. So now you know the
Yes.
You know. So we have estimated this,
Yes.
this, and this.
So you
So
just
then
invert it
we
back.
generate first. We generate phi,
Yeah.
j, and then in cascade we generate.
Okay.
So we go back.
So sorry, another trivial question. So like if I want to think about, if I want to sort of naively map this onto how one does it, how one does deep neural networks, it's taking an input of some sort and having sequentially layers that sort of have that are wider and wider.
Yes.
And so that the last layer is sort of supervised,
Exactly.
and then you sort of get it back. Okay.
Now these are the example of the energy. So this is the double well that we estimate from the data. Now what you see here is, so j equal 4 is the largest scale, j equal 0 is the smallest scale. So what you see here is exactly what the inverse of what you see in an RG flow. In the RG flow, typically you start with the potential, which is a double well. When you do RG, then it becomes just a quadratic because of large scale, you have a Gaussian. Now here we do it's the inverse. This is a high temperature. So we start with something which is just quadratic, and then while you go down in RG, you retrieve more and more information. At the end, you get the potential, which is a double well, as it should be, because we know that we generate the system or the configuration using the double well. So this is the example at above TC. At TC, while you see, the images are small, but you see the existence of the fixed point, because you start from you start at the beginning from something which has already a double well structure, and then the system flow to something at which it remains for some scale, and then it goes away and it goes to this, which is just a microscopic double well. Okay, so if the system was very, very big, what you would see is that we first see some flow. So maybe I can show here just to remind you. So in RG, what you do is you go, you start from a certain value, then you go very close to the critical point, and then you go away. What you're doing just the reverse. You start from the high temperature, for example, you go very close to the critical point, and then you go on the other. You go back to the microscopic. Okay. So now this is the case which I find also very, very interesting. It has to work, but at the beginning I thought it was something really interesting. Is that still think that is interesting. So here is below TC. And what we do here is that we feed to the system configuration which are all positively magnetized. So the system lives in a world in which all configurations are positively magnetized. Doesn't know that there is a symmetry. Doesn't know that there is a symmetry breaking. Then we run the inverse RG, and what you go from a potential which is like this to a double well. So here there is just a cut because we have a cut here. But what you see is that the system actually is able to reconstruct the fact that the microscopic energy was asymmetric. So it knows, just looking at configuration that all broke the symmetry, knows that actually there was an underlying symmetry that is broken, and the underlying system was symmetric, which, well, to me, it's, and the reason why he's able to do this is that when in the configuration, you have small scale fluctuation. So in order to, if you want to reproduce the statistics well at all scale, the system is, even when configuration are positively magnetized, you have small fluctuation on the other side. And in order to correctly describe the small scale fluctuation to the other value of the magnetization, well, you must have microscopically a correct double well. This is what you retrieve. And here is the comparison between the true and the reconstructed, because in this case we can test whether we are good or not. So here is the double well reconstructed and the true one at the critical point. So you see it's perfectly reconstructed. And this is the eigenvalue of the discretized Laplacian compared to the eigenvalues of this bilinear operator K. That here it's very good too at the critical point, which is the most difficult case. Now, the other thing which is important now is I insisted a lot about the fact that we can train the system on time scale which are order 1, and we can sample new configuration on time scale which are order 1, even at the critical point. And here is the I'm going to show it numerically. So this is the correlation function of the field phi of the microscopic field phi. So this is just what you're seeing here. This is for different temperature approaching the critical point. So what you see here is the critical slowing down. When you approach DC, well, the time scale to equilibrate the system, so to decorrelate from a given configuration, is larger and larger. Here is what you see for the same thing, but when you do the Monte Carlo Markov chain on the wavelet field. It's the correlation function of the wavelet field. While you see nothing, there is nothing whatsoever when you approach the TC. Actually, well, if ever, it's even faster when you approach TC, but I think this is it's just the time scale is of order 1. And here is the comparison between the time scale at which it takes to generate a sample with standard Monte Carlo at TC and the time it takes using the wavelet RG. So this is the usual critical exponent that you have for critical slowing down, and here you see there is nothing. Now this is for the training. So if you want, here is what when you train is the kind is the typical behavior of the loss. There is a loss function that you minimize when you do the training by minimizing maximum likelihood. And so this is the behavior. If you do it, if you try to estimate the energy in one shot. So you say, I have the probability of the microscopic field. Let's say that I say this is exponential minus an energy. I try to fix the value of the energy, not in a multi-scale way, but just directly. So this is something that is long, and it's the larger the system, the longer it will be. And here is what you get is in our case, which is the conditional RG. Again, the time scale is very fast. I didn't show different system size, but it's just for one system size. So this is just a test to show you that indeed the method is well conditioned. It's applied math sense. So even if you take a system which is much bigger, the training will be on the same time scale. And from the point of view of physics, the nice thing is that we can generate with this method new sample on time scale which are just of order 1. So here I put order n because from computational complexity, with the number of operations that you have to do is n, but the relaxation time in physical sense is of order 1, even at criticality. Okay, so maybe actually I will I almost skip the part with cosmology, and because I want to discuss something else before concluding. So we applied the same on cosmology. So in cosmology, we don't know what the energy function is, but we find, so this is the example training data and the sample. Here I wanted to show, so one way, of course, is looking visually to see whether we are doing well or not, but another one, which is more, is looking, for example, at the histogram, the probability distribution of the value of the field at a given point. And here is the comparison between the training and the synthesis. So you see, it's on a very different scale. The probability distribution is very well captured. It's the probability distribution of the field phi I on the microscopic scale. And here is in this case, what I wanted to tell you also is that you have to introduce, actually, it's necessary to introduce this B-twiddle, which are this new energy term, which are local on scale J. So they give local interaction of the fast degrees of freedom, that they produce actually long-range interaction on the microscopic scale. So here the energy for this system is an energy in which we have long-range interaction at all scale. But they can be represented by small-scale interaction between the fast degrees of freedom at each scale.
The map you're showing is the mass distribution or the effective potential?
So it's this one?
Yeah.
Well, this is the mass distribution, put on QD, yes, taking into account also that things arrive in the
So you, since it's from weak lensing, you
Yes.
potentially have also the shear field.
Yes.
So you could see whether your technique works also in a vector field
Yes.
or
Yes.
bivect.
Yes. Okay, and so actually, well, the result that we have here are really comparable to the result that we obtained with other techniques, including, I mean, generation using deep learning techniques in this case. Okay, so what I want actually to leave some time for the discussion and give you, I mean, first the conclusion and then tell you where we are heading, what can we do more, and maybe try to generalize the method. So I mean, to summarize, what I try to show you is that if you consider images which come from physics, which means that there is some underlying hypothesis on the locality of interaction between fast degrees of freedom at each scale, we can actually answer to the different questions that I asked at the introduction. So we have constructed method, which is a multi-scale method, which goes from large scale to small scale. You retrieve from the data information about the probability distribution scale by scale. And in this case, we show that it reproduces, I mean, we ask whether the representation is faithful, and we know that yes, it reproduces accurately the underlying probability distribution in the case in which we know it. We show that in this case, is efficient and stable, even in presence of long-range correlation, and we understand why. The reason is because we always work again on what are the fast degrees of freedom on each scale. We're able to reconstruct the energy, something that you cannot do, for example, with generative models which come from artificial neural network. And I think in this case, we really understand why it works. It's really related to it's a combination of and this is one of the things on which I want to insist. It's a combination of the property of the data and the property of the method. So the method works scale by scale, working always on small scale fluctuation. Then, of course, this is not going to work on any kind of data, but for the data which come from physics, in which indeed there is this hierarchical structure with small scale fluctuation at each scale, which are easy, as I show you in an image. So the method can work. And this, I think, is really, I mean, it's the challenge to understand why machine learning works is really a challenge in which, of course, machine learning is not going to work for anything. And when it works, it's because the algorithm encodes some structure, they have some inductive bias, they encode some structure in the data. And this, I think, is one of the first cases, the first step, to try to put together what there is in the data, what there is in the algorithm. So here we see that there is a hierarchical structure in the algorithm, and there is a hierarchical structure in the data, and the two combined together lead to a good sampling, an efficient method, and a method that is able to generate good sample. Yeah.
So as someone who doesn't really know much about generative AI models, do other models also produce some probability distribution? So if you use another popular generative method, it produces some probability distribution, correct?
Yes.
And
well, typically, many methods, what they do is that they produce sample.
Okay.
Then you don't get the energy, but then there are also some that come from which you get the energy.
Okay. 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 My question was then going to be, if they did produce a distribution, and could you not just take the log probability distribution, and that gives you something? But you're saying they don't give you the distribution at all.
No, they give you a sample. Okay. All right. So now, what about more complex data? So, what are the limits, or how we can generalize the model? So first, what about real images? And so there is a very nice work, which is a follow-up in the context of computer vision of what we did by Stefan Malayer, Simon Stanley from Paris, and I don't know the first name of that, which is applying the same idea, but now to images. I mean, does it work or it doesn't? And again, so the idea is the same. So we take the probability distribution, we assume that there is a probability distribution, and we rewrite it in this way. And so what they do is that now they want to infer each one of these conditional probability. So of course, even for a bold physicist, thinking that this can be represented like a bilinear term and a double well would be a little bit too much. But I mean, what you can do is that I think, and this is really the essence of the method, what you can do is that you can think that this is going to be represented by an effective energy function in which you have only local interaction between the field psi. And this is what they do, really. So what they do is that they use a CNN, so a convolutional neural network, with a very small receptive field to represent the conditional probability distribution. So in practice, what they do is that they do, so first they have the hypothesis that the effective energy of this is local, and then that this can be well represented with a convolutional model. So this, I think, is the essence. And if we want to generalize the model, the essence is this, whether or not this for more general data is represented by local interaction. So this is what they assume. So they use they infer the probability conditional probability at each scale. And now what they find is that if they do this, they can do, so this is a good thing to do, but they have to stop at a certain scale, meaning that if you have an image, so let's say 300 by 300, for example, you can do this, and indeed the conditional probability is local until you arrive to something which is, I don't know, a coarse grained image, which is 10 by 10. And there you really have to use a completely a convolutional network with a very large receptive field, meaning that on that scale, really the interaction are very long range, which I think it gives an interesting message in the sense that it tells you that within the kind of images that one studies, there are many small scale properties until very large scale that you can capture with a local model with of the interaction between the small scale fluctuation. And then only on very large scale, you need something which is more abstract. And in a certain sense, it's normal. I mean, in an image, you have some hierarchical or some relation between the objects, like one nose, etc., which goes beyond, some property in local space. So this seems to say that in but it seems, it doesn't mean that, this is where it's where we are now, is that indeed the probability distribution for images like this, as can be represented like a cascade with local interaction until the large scale, and only at the large scale you really need a convolution, one complicated artificial neural network. Otherwise, at the all other scale, actually, the understanding can be easy, and you just have local interaction. So this is one thing, and I think it's the important message, not generalization of what we did. What we do is considering local model for this conditional probability, which goes beyond what the simple expression that we use. And the other thing that I would like we're doing is to apply this to non-equilibrium physics. So in a certain sense, cosmology, weak lenses is already an example of non-equilibrium physics, but I have to admit that I understand better, for example, models from non-equilibrium models, non-equilibrium physics from statistical physics than non-equilibrium physics from cosmology. So this is why actually we are focusing on this. What we want to do is that we want to get data from, indeed, for example, active matter. So here is an example of, this is a model, very simplified model of active matter, in which you have, depending on the, you have a system which is a non-equilibrium steady state. It's out of equilibrium because the dynamics is not time reversal. But in some cases, it can show a physics which resembles the equilibrium one, like the separation in this case. And it shows something, a physics which seems to be very different from what you see in equilibrium. And what we want to do is that we want to apply the model, and what we want to, well, first show that we can generate new sample in a faithful way, but then especially we want to study the effective energy function. And really, what I'm really interested in is, well, maybe two different kinds of things. One is that with this method, we can do RG directly from the data. So in generally, the usual way to do RG is, well, you take the model, first, you know from experiments that there is an interesting phenomenon to explain. Then you try to think hard what would be the simplest model. Then you try to think hard what would be the approximation to try to do the RG. And here instead, it's the idea, of course, you have to do some hypothesis on the kind of model that we put in the wavelet RG, but then otherwise we just work from the data, which come directly from simulation or from experiments. And so we can study, we can do RG then for non-equilibrium system using this data. And also we can study what is the form of the probability distribution, or more correctly, the energy. So something that I really would like to know, in which case actually systems which are out of equilibrium are described by energy, which have long range interactions necessarily, and cases in which they do not. And I think with this, I thank you for your attention, and I stop here.
Very nice talk. So a lot of questions. Let us ask one for the start. This notion of sort of expanding and getting something very generative, it somehow reminds me of the kind of things that go into transformers and architectures like that? Have you thought about analogies between things?
There's an analogy between
Your thing and transformer? Yeah.
No, not really. See if I can. I mean, yeah, I don't know. I have to think whether the mechanism of attention can be understood in the system. So some analogy can be done.
Okay, and stop for now.
Peter.
Yeah, thanks for the great talk. I guess I had a question about this wavelet decomposition. So my understanding is when you do real space RG, choosing how you coarse grain is really important. And it seems like doing this wavelet decomposition is like one choice of how you coarse grain. So I'm wondering, is there a sense in which there might be cases where you do have this kind of local structure, but this wavelet decomposition is not the correct way to coarse grain?
So, okay, maybe to answer. So the first one is something that I actually didn't understand until I work on it, is that the wavelet is really nice in the sense that when we do, so wavelet is a basis which is localized in real space and in Fourier space. Somehow when we do RG, we are used to either we use Fourier space, which is nice for analytical computation, or we use real space, which is well, not nice when in real space. Now, there are good and bad for both. I mean, real space is nice, like I mean, the Kadanoff method, because well, it's simple and it's versatile. It works well in low dimension. It works very bad in high dimension. For example, you cannot get the apophysical dimension because actually you represent very badly the Laplacian with this kind of methods. Now, if you take Fourier, great in high dimension, and then you get the apophysical dimension. Then, well, if you want to go below, well, you don't know. You do epsilon expansion with epsilon, which is big. They are not well adapted to low dimension. Now, the thing which seems really nice is that using wavelet in the way in which we discuss, maybe doing actually forward RG instead of inverse RG, is really a method to combine the good part of Fourier and real space, in the sense that it's a real array space method, but if you choose carefully the wavelet, this is known from wavelet theory, you represent very well the Laplacian, so you can get things which are very good also in high dimension. So this is one part of the answer. The second part, I think, is related to an answer that was asked before. I think the wavelet are very good to get this, to represent this small scale fluctuation, especially if you choose carefully the wavelet, the type of wavelet. This, of course, is okay as long as in your data, you have a structure in which you have a coarse grain field with small scale fluctuation with just local interaction. So if you don't have this, then indeed the model is not going to work. And maybe you cannot even cure it using the correct wavelets.
So what's the kind of the strategy for choosing the wavelet?
So in practice, I think it's you have to choose wavelets of an order which is, so for example, just the Kadanoff method, it's again something that I should have known, I didn't, correspond to what are called R wavelet, which is, so in wavelets, you have, let's say, a kind of different degree, and there are, let's say, the simplest one, which are the R, which very bad to represent the Laplacian, and then you can get things which are a little bit, so the more they are long range in space, the more actually they can represent well the Laplacian. So in our case, actually, in order to prove also the theorem center, we have to choose wavelet of a certain order in such a way that we know that the property of the fluctuating field, let's say. So at a certain point, we use something about correlation in space of the wavelet field. And in order to be sure that short range correlated in space, we have to choose carefully the wavelets, otherwise it won't work.
Yeah, so I imagine that the number of samples you take sets some kind of length scale in the system. Is that accurate?
Why length scale?
Well, okay, if I have, you said we have 32 by 32.
Yeah.
You had some tens of thousands or hundreds of thousands. So the number of degrees of freedom compared to the total number of samples is like this classical ratio that you use for determining whether you can use asymptotic statistics or unasymptotic statistics, right? And so I imagine as I add degrees of freedom to the system, eventually I'm going to have many more spins, let's say, than samples, right? Is this something like?
So in practice, okay, maybe to answer, the first one, so what matters is the number of parameters that we have to fit. And this, it's a fixed number because we represent the energy with a bilinear term and the potential. So this doesn't scale. So if I see a system which is bigger and bigger, in principle, the number of parameters is not going to grow. So it's what I mean, the trade-off is really between the number of data that you have and the number of parameters. Then in reality, I don't know how would it work in this case, but in reality, in real deep networks, they work in a regime in which the number of parameters is much larger than the number of data. So they escape from the classic, let's say, bias variance trade-off in which you should take a number of parameters which is not too large. But in our case, since we have a model in mind, we can use a number of parameters that doesn't scale with the system size.
I guess what I'm wondering though is if we're talking about inference or flowing back up the RG in some sense, and you're in some undersampled regime, you know, how would that look different from or similar to the case where you have well-sampled data? Like would your inferred potential start to do poorly in the undersampled regime?
I had much less data.
Yeah.
Yes, if I at a certain point, if I had much less data, I would sample well the double well. But I mean, the good thing is that since we have a model, the number of parameters is much less than the number of data, and we don't need in any case much data because 10,000 is not so much in this case. I mean, but yeah, if we degrade the number, if we decrease the number of samples at a certain point, and this is something that we didn't study. So given what we are doing, how small is the number of sample? I mean, what is the minimal number of samples that we should use in order to have good results, and what is that controls this number? So this is something that we study.
Okay, perhaps in the interest of time, we just stop here, and thanks to you again.
One thing is learning the wavelet from them. Which is very
So I thought that's what so I'll see you at 12 in the other hand.
Yes, so I also want to should put it in data science.
Yeah, I saw you like Monday or something. Yeah. Yeah,
That's why.
Trying to use like some machine learning to do real time. I don't know what point is that. I know there was this one where they use like spaces. And then there was another one where I think
it's quite on the right.
Yeah, one.
Yeah, but actually making you. I got it.
Try to get the information.
Yeah.
They change the scale. I mean, but you're right.
But I don't know.